Amedeo Avogadro, in 1811, took two gases. He took hydrogen and he took oxygen. He noticed that he had the same volume of each. He had 2 liters. They were measured at the same temperature and pressure. The ATM here means atmosphere, and it's a pressure unit. And when he weighed these samples of gases, the oxygen weighed a lot more than the hydrogen. Now, Avogadro made a famous hypothesis. He thought that equal volumes of gases, measured at the same temperature and pressure, would contain the same number of molecules. Now that's key, that they contain the same number of molecules. Not that how many molecules they contained, but that they were the same. Because this way, he could actually figure out how much heavier one gas was than the other. And so, since oxygen weighed more, he knew that oxygen, and he called everything pretty much molecules then, had to be heavier than hydrogen. So I'm just going to use the word atom because we know that's really the true word. So if he took the mass of oxygen and divided it by the mass of hydrogen, he got 16. And what this meant to him was that if each hydrogen atom has a mass of 1, then each oxygen atom would have a mass of 16. Now you notice that he's not saying grams or anything else. So these numbers that he came up with are called relative weights because they're comparisons. He compared it to hydrogen because hydrogen was the lightest element known at that time, and it still is today. Now we have to give weights some sort of a unit, and so a unit was created called an atomic mass unit. Now at the time it had no relationship at all to grams, but later on they were able to make a connection between grams, and it's extremely small, so it's best not even to bother with it. So here are some relative weights. So if hydrogen has a weight of 1 AMU, oxygen would be 16 AMUs, carbon 12, sodium 23. The important thing to note is that these numbers are not real masses, they're just relative numbers. You can see then that sodium atoms are almost twice as heavy as carbon atoms. That's what it means to be relative. We're not saying how much each atom would weigh at all. That came about later. How many atoms would you have? It was much later that this was actually determined. So let's take a look at some samples. All right, I have carbon on the left. Across from that is sulfur. Below that is iron. To the left of iron is copper. And in the middle I have some mercury. Now all of these elements, their atomic masses are weighed out in grams. So for carbon I had 12 grams. You see the number of carbon atoms. Don't worry about where the number came from. You don't have to figure out where it came from. We're just going to be using this number. For sulfur, 32.1 grams is its atomic mass. You notice that we have the same number of sulfur atoms. Mercury, 200.6 grams, same number of atoms. Copper, that's its atomic mass, and iron its. So what do we notice? If you weigh out the atomic mass of an element in grams, you'll have 6.022 times 10 to the 23rd atoms. So it doesn't matter what the element is. If you weigh out that mass, that's how many atoms you would have. Now nobody would pick that number. That's just the way it turned out to be. The point is we already had these average atomic masses, so instead of throwing them out completely, people wanted to keep using them. So this number, 6.022 times 10 to the 23rd, has 2 names. It's called 1 mole, and it's also called Avogadro's number, symbol capital N sub capital A, in honor of Avogadro, even though he's not the one that determined it. All right, let's use our new information about moles and grams and Avogadro's number in some questions. So we start off with carbon with an atomic mass of 12. If I had 12 grams of carbon, that would be 1 mole of carbon. Why is it 1 mole? Because its atomic mass is 12. So 12 grams is the mass of 1 mole of it. And then by definition, I would have Avogadro's number of atoms. If I doubled my mass to 24 grams, that would double the number of moles and double the number of atoms. That makes sense. If I were to triple the number of grams, I'd be tripling the number of moles. So I'd go from 1 to 3, and I'd be tripling the number of atoms. And that makes sense as well. if I took my 12 grams and then only measured out 1/100th of it, then I would have only 1/100th of a mole and 1/100th of the number of atoms. So you see, it's kind of like a ratio. But what if I had 16 grams of carbon? It's not quite simple to see what the answers would be here. But what we're going to do is use the atomic mass to figure out first how many moles and then how many atoms. Well, I know that 16 grams is in between 12 and 24, so my number of moles is in between 1 and 2. So I'm going to take my sample mass and I'm going to divide it by the atomic mass. And when I do that, I get 1.33 moles. And then I just have to multiply 1.33 times Avogadro's number. Now, if you were given a question like this to answer, you would actually multiply your number of moles by Avogadro's number. You wouldn't leave it like I am. Here's a couple of other questions based on aluminum. And in the picture there, you see aluminum, a foil being produced. Aluminum is extremely malleable. They kind of run it through rollers in order to produce the foil. So let's start off with the question. Right? How many moles of aluminum atoms are in 2.70 grams of aluminum? So the question then is 2.70 grams of aluminum equals X moles. All we have to do is look up the atomic mass of aluminum. And if we do, we're going to find is 27. So my setup is going to be 2.70 grams times 1 mole of aluminum over its atomic mass. And you notice how the grams will cancel, and I wind up getting 1/10 of a mole for an answer. And I'm keeping my number of significant figures near consistent. So I started with 3 in 2.70 grams, and I'm writing 3 at the end, my 0.100. Now the second question, how many atoms of aluminum would this be? I'm going to take my answer from the first question and multiply it by Avogadro's number. And now moles will cancel, and I get atoms for an answer. You notice that it's the power of 10 that's changing. Okay, next question. This time we have neon that we're being given, grams of neon. And we want to know how many atoms of neon that would be. So the way we're going to solve this is not to go directly from grams to atoms, but we're going to go through moles. So what I want to do is convert my grams of neon to moles of neon. And to do that, I need the atomic mass of neon. So I have to look that up. And once I have moles of neon, I can use Avogadro's number to give me atoms of neon. So here's my solution. So taking my 0.125 grams of neon and multiplying by 1 mole over its atomic mass, you see the grams will cancel. I'm not going to do the math until the end. And now I'm multiplying by Avogadro's number. And again, moles of neon would cancel now. And here's my answer. Now here's one for you to try. How many moles of potassium atoms would weigh 2.50 times 10 to the negative 4th kilograms? So there's your question. Now why don't you pause right here and see if you can answer this one, and then come back and pick up on it. Well, okay, here's the solution to it. First thing I'm going to do is take my kilograms of potassium and convert that to grams. So you have to remember that there are 1,000 grams to a kilogram. And then I just need to use the atomic mass of potassium to convert that to moles. So here's my setup. So starting with kilograms of potassium, converting that to moles, so multiplying by 1,000. Notice the kilograms cancel. And then I'm multiplying by 1 mole of potassium over its atomic mass. And I get a number like that. Now you notice that this is a very small number, but I would expect that because this is a pretty small mass. Now here's a question that people could never ever answer by going into the lab. What's the mass of one atom of any element? In this case, it's uranium-238. But we could never weigh that. In fact, we couldn't even see one atom, really. But we could figure out how much it would weigh. So here's my question. 1 atom of uranium, how many grams of uranium? So my plan is to convert 1 atom to moles. It's going to be an unbelievable small number of moles. And then, once I have moles, I can use the atomic mass to give me grams. So here's my setup. So I start with my 1 atom, and this time I'm multiplying by 1 mole over Avogadro's number. The atoms would cancel. And then here is the atomic mass of uranium. You notice it's 238, and that gives us the mass. So the mass of one atom, 10 to the negative 22nd, that's really, really small. So even if the question had said, what is the mass of 100 atoms of uranium, we would do this exact same setup. Now, one of the things you usually ask to find is the molar mass of a compound. And molar mass means the sum of the masses of the elements in a compound. For an element, we could just say the molar mass is its atomic mass in grams. That also works out. So here's an example using water and CO2. If I want to know how much does 1 mole of water weigh, I have to take my formula and break it down so I know how many atoms of each element are in the formula. So we have 2 hydrogens and 1 oxygen. And I'm going to multiply the number of hydrogens by its atomic mass, which is 1. And I'm going to add the atomic mass of oxygen to that. And I get an answer of 18 grams per mole. Now, grams per mole is the unit for molar mass. And it's read as the mass of 1 mole of an element or a compound. In this case, it's a compound. And notice I'm doing the same thing for carbon dioxide. 1 carbon and 2 oxygens. The atomic mass of a carbon is 12, plus 2 times 16, the atomic mass of oxygen, and I get a molar mass of 44 grams per mole. It's pretty easy to do. In fact, since it's so easy to do, many students do it wrong when we need to do this in solving other questions. So go through this slowly, because that's the most common error is on molar masses. So here's a couple for you to try. I'm giving you the formulas and the names. Why don't you look up the atomic masses and see if you can figure it out. Okay, so these are the answers. I hope you tried on your own. For magnesium hydroxide, you notice when we look at the formula that the 2 outside the parentheses is multiplying everything in it, but it's not going beyond the parentheses. So there's 1 magnesium, 2 oxygens, and 2 hydrogens. And then just substituting in the atomic masses, I get a total molar mass of 58.3. The glucose is going to be even easier because there's no parentheses. I get a total molar mass of 180. Now let's see if you remember how to write formulas first. So the first one should be no problem. Tetraphosphorus hexoxide. So what's its formula? So we can figure that out. Calcium phosphate. You want to look up the ions. Now if you don't remember them, calcium is Ca plus 2. Phosphate is PO4, charge of minus 3. Sodium bicarbonate, Na positive 1, HCO3 minus 1 for bicarbonate. So if you want to take a minute, let's see if you can figure out the molar masses. Alright, here we go for the answers. Tetraphosphorus hexoxide is P4O6. So that's 4 times the atomic mass of phosphorus plus 6 times the atomic mass of oxygen. We add them up and we get 220 grams per mole. Now you might want to do I have to memorize these atomic masses? And the answer is no. But you should get familiar with the common ones, like the ones that we're using so far. The calcium phosphate, did you get the formula right? Ca3, PO4 parentheses 2. So that's going to be 3 calciums, 3 times 40.1, plus 2 times the phosphorus, 2 times 31, plus 8 times 16. So you notice it's 04 times 2. We get a mass of 310.3. Now for the most part, I like to keep a number in the tens place, as long as it's not a 0. Different people round up differently on this. So sometimes, if you look at answers in the back of the textbook, they might be slightly different than what you wrote down, but that's fine. Sodium carbonate now, NaHCO3, give us a total mass of 84 grams per mole. So finding the molar mass is one of those skills that most people pick up pretty quickly. Now we're going to use those molar masses in answering questions about moles and atoms and molecules. So the first question is about sodium chloride. So what would be the mass of 0.905 moles of sodium chloride? Well, it's almost 1 mole of it. So if you figured out the molar mass of sodium chloride, you know that your answer has to be a little bit smaller than that. Now we're going to need the molar mass of NaCl in figuring out the question. So all I have to do now is take my number of moles that I'm being given and now I'm going to multiply it by the molar mass. Now you notice the number of moles will cancel. And this makes sense, because if 1 mole is 58.5 grams, 0.9 moles should be a little less than that. Why don't you try this one for glucose? We already did the molar mass of it in the previous slide. How much would 1.5 moles of glucose weigh? Again, you could figure it out without even writing it down. The molar mass is 1 mole of it, plus a half of it would give you the answer. To do it all out, we would take our 1.50 moles and multiply by the molar mass. Again, moles will cancel. 270 sounds right. But again, you can figure it out in your head for this one. If 1 mole is 180 grams, and a half of 180 is 90, that means then 180 plus 90 would be 270. Well, let's take a look at a question involving water, since water is so common, and people probably have liter bottles and 2-liter bottles of water. I bet some of you even have in your bag bottles of water. So could you figure out how many moles of water are in a 2-liter container? So 2 liters of water, how many moles of water would that be? Now, we don't have a connection directly between liters of a liquid and moles. We always have grams to moles. So we want to figure out how much would 2 liters of water weigh in grams. So if we use the density of water, which is 1 gram per milliliter, we could figure that out. So we're going to go from liters to grams to moles. So here's my solution. Now, first of all, I want to change my liters to milliliters, and that's because my density is 1 gram per milliliter. So I have 2 liters then would be 2,000 grams. And 1 mole of water is 18 grams. That's 111 moles of water. That's a lot of moles. Or remember, water molecules pretty small. Could I even count the hydrogen atoms in that? Well, I could. If I know how many moles of water I have, and I look at the formula for water, H2O, that tells me that for every mole of water, I have 2 moles of hydrogen and 1 mole of oxygen. So all I have to do is take my number of moles of water, multiply that by 2, and that'll give you moles of hydrogen, and then use Avogadro's number. So there will be 222 moles of hydrogen times Avogadro's number, get a pretty big number of atoms. So this is a way that I can count the atoms in a sample of a compound. So you notice that when I look at the formula for a compound, it has more meanings than I thought. Besides telling me how many atoms of each element are in one particle of it, it also gives me the ratio in terms of moles. So moles and molecules are similar in the sense that they mean the number of particles. Molecule means 1, mole means simply Avogadro's number of it. But the ratios between the particles remains the same. It's for hydrogen and water, it's 2 to 1, whether it's moles to moles or atoms to molecules.